Why are the stars and planets spherical? Why do all huge celestial bodies have a spherical shape? Are there any huge celestial bodies that aren't spheres? Celestial objects can take on odd and irregular shapes as long as they are tiny enough. However, there is a mass-dependent limit beyond which every object tends to take on a spherical shape. Above this point, the force of gravity outweighs the cohesive force of the bigger surface structures, and any major prominence is dragged toward the center of gravity with sufficient force to destroy it. As mass grows, so does the surface force of gravity, and the shape of the celestial body becomes more spherical. Of course, tiny disuniformities will always exist because the sphere is a geometric abstraction. Is that truly all there is to it? Let us find out together. How many planets are there in the universe? A lot. It is expected to be around 1 sextillion. Do you know how much 1 octillion is? Quite a lot. A number so big, a billion trillion, that it is difficult to imagine. Consider this. The planet Earth weighs approximately an octillion times more than a walnut. However, all of this infinite is made up of objects that have one feature. They are all spherical. There isn't a single cuboid, dodecahedron, or heart-shaped one to speak of. But why? First and foremost, it is important to remember that we are discussing planets rather than celestial objects. The term celestial bodies refers to a wide range of objects with varying properties and shapes that, for a variety of reasons, might diverge significantly from the spherical shape. Consider our galaxy, the Milky Way, which has a disc-shaped structure rich in gas and stars within a so-called halo, comprised of stars spread in a more or less spherical shape. On the other hand, if celestial body refers to particular objects such as stars or planets, it is true to remark that the typical shape is roughly spherical. The rationale is likewise fairly obvious. All the most massive planetary objects, whether stars or planets, are generated by the action of gravitational force, which is the force that attracts the constituents of matter to each other and subsequently to the center of the expanding body. And if myriads of particles are drawn to a single site of aggregation, they can only result in a spherical agglomeration. And the larger the mass being assembled and the lower its density, the more the final outcome resembles that of a perfect spherical. The physical principle involved is similar to that which causes soap bubbles to be spherical and fat bubbles in broth to be circular. Nature always chooses the shape that requires the least amount of energy. In fact, for the same volume, the sphere is solid with the smallest surface area. As a result, the soap bubble prefers to form a precisely spherical shape. It does, in reality, attempt to organize itself into the shape that requires the least amount of energy to sustain itself. Leaving soap bubbles and returning to planets, we can conclude that extremely high gravity precludes any surface roughness from exceeding a particular height. For example, mountains greater than around 10 kilometers cannot exist on Earth because they would gradually sink in on themselves, reducing their size. As a result, with its bulk, the Earth could never have a rougher form than it has, save for the little time required to level out the irregularities. The maximum surface roughness on neutron stars, stars with 100 billion times more surface gravity than Earth, is expected to be less than half a centimeter in height. When the dimensions are compared to the Earth scale, it appears that no mountains on our planet can be higher than 5 meters, the level that maintains the shape of an object that meets the physical parameters to be named a planet. The so-called hydrostatic equilibrium is nearly perfectly spherical, a state in which the gravitational attraction that draws matter to the center is balanced by the thrust caused by material compression. The notion of hydrostatic equilibrium also allows us to establish whether a celestial object is a planet, a dwarf planet, or a small object like an asteroid or comet. In fact, according to the new definitions established in 2006 by the International Astronomical Union for our solar system, planets and dwarf planets must have a spherical shape and have reached hydrostatic equilibrium before they can be recognized as such. But how large must an object be to reach hydrostatic equilibrium? It depends on what it's built of, namely the density of its upper layers. Gravity is a relatively weak force. An object must be extremely large before it can produce a gravitational attraction strong enough to overcome the resistance of the material it is comprised of. This, incidentally, is why you don't have to worry about your bodies collapsing into a sphere at any time. Anyway, let's try to get some order into everything. Although many factors influence the shape of an object, there are only three sorts that frame the problem. Objects about 400 kilometers in diameter. If such an object has a snowball density or around 1 gram per cubic centimeter, it will be able to form a spherical shape. For example, Mimas has a diameter of 396 kilometers, making it Saturn's 7th satellite and the 21st largest in the solar system. It is also the smallest celestial body with a spherical shape because to its extremely low density, 1.15 grams per cubic centimeter. This example highlights a crucial distinction: being spherical versus being in hydrostatic equilibrium. The crash that formed the massive crater that resembles the Black Death left an imprint that Mimas gravity cannot erase. However, sphericity alone is insufficient to make you a planet. You must also establish hydrostatic equilibrium. Objects of equal size but higher density will have more or less irregular forms. For example, Pallas and Vesta are two huge asteroids in the main belt that, despite their diameters of more than 500 kilometers, have a form that is far from spherical due to their extremely high density. Objects with sizes of approximately 1,000 kilometers. This size typically results in a spherical shape but does not guarantee hydrostatic equilibrium. If the object is thick and subjected to a large deformation event, such as an impact, gravity would most likely fail to close the wound, resulting in a loss of overall shape. Surprisingly, Saturn's odd moon Japetus, with a diameter of up to 1470 kilometers, is the largest known entity that is not in hydrostatic equilibrium. Despite its low density, which should make it easier to mold into a sphere, its silhouette is defaced near the equator by an uninterrupted mountain range. Unbroken and incredibly mysterious, as its origin is unknown. On the other hand, what is the smallest spherical object in the solar system that is in hydrostatic equilibrium? It is the largest asteroid, the dwarf planet Ceres, with a diameter of 940 kilometers. Other spherical objects of this size in hydrostatic equilibrium appear to be Orcus, 916 kilometers, Salacia, 846 kilometers, Quaoar, 1,120 kilometers, Gonggong, 1,230 kilometers, and Sedna, 995 kilometers. Objects with a diameter of around 1,500 kilometers except for Japetus. All objects this size or larger are completely spherical and balanced. All of Jupiter and Saturn's huge moons come into this group, as do Uranus, Titania, and Oberon, Neptune's moon Triton, Pluto and Eris, and of course our own moon. In summary, including the Sun, there are approximately 30 spherical objects that meet the balance criteria. Then there are literally millions of small bodies more akin to flying mountains with extraordinarily different shapes. Lumps of boulders assembled in the most rambling of ways, such as Comet Churyumov-Gerasimenko, visited in 2015 by the Rosetta probe, or the small asteroid Itokawa, visited in 2005 by the Japanese probe Hayabusa. Not to mention items whose shapes defy classification. And I'm thinking about the menacing shadow of the interstellar visitor Oumuamua, which has sparked infinite speculation about its origins as it travels through our solar system. Or consider the odd flying saucer shape of Pan, Saturn's small moon wedged between its rings. That's all clear. Practically speaking, gravity has both advantages and disadvantages. But gravity isn't everything. While gravity conspires to make planets spherical, the speed of their rotations works to flatten them. The faster a celestial body rotates, the more exaggerated its equatorial bulge is. This is why our solar system has no perfect spheres, only oblate spheroids. Jupiter would be entirely spherical if it did not rotate, but unfortunately it rotates swiftly on itself every around 10 hours, resulting in an equatorial diameter that is 10% bigger than its polar diameter. Similarly, Saturn and Venus, which rotates very slowly on its axis every 243 days, is the most spherical planet of all. Even the Sun, with its massive gravity and relatively moderate rotation speed of 25 days, can be called a perfect sphere. However, a large proportion of stars in the sky rotate much quicker and swell significantly at the equator. The case of Achernar, the 10th brightest star in our sky, is instructive. Its rotation time is 2 days compared to around 27 for our Sun. To make matters worse, the star is far larger and more massive, with an equatorial velocity of at least 250 kilometers per second, 125 times faster than the sun. Faster than that, and the star would collapse. This tremendous speed creates an intense centrifugal force, flattening the star and making its equatorial diameter 11 times that of the sun and 56% greater than the pole. In terms of flattening stars, it is in good company. There are several unusual revolving stars, including Regulus, Altair, and the well-known Vega. Red supergiants, like as Betelgeuse and other massive stars, may have a nearly spherical shape but have significant surface modifications caused by the convective rise of hot gas, which forms gigantic, irregularly shaped bubbles on their surfaces. And I'd like to finish by mentioning galaxies again. They too have a wide range of shapes due to their rotation. If their global rotational motion were zero, they would take the shape of globes, as do spheroidal elliptical galaxies and globular clusters. In short, there are never dull moments in space. Don't you agree? Let us know what you think in the comments below, and remember to like, share, and subscribe.